Before we move on to transformations, we need to establish some properties of trigonometric functions, both graphically and algebraically. By the end of this particular lesson, you should be able to look at the graph of a wave and identify the amplitude of a wave, both graphically and algebraically. We'll begin by again observing a singular sine wave as it extends from 0 to 2 pi radians. Now, because we haven't applied any transformations to this function, we have what's known as a baseline of y equals 0. You can think of the baseline as an imaginary line that sits kind of in the middle of the wave. In fact, the value associated with a baseline is exactly halfway between the sinusoidal wave's maximum value and its minimum value. Conveniently, knowing these values also provides us with a key property of sinusoidal functions, the amplitude. The amplitude is defined as half the vertical distance from maximum to minimum. Simply find the difference between the maximum and minimum, here we have 1 minus -1, and then divide that by 2. In overly simplified terms, the amplitude effectively tells us how big the wave is. Now, everybody here has experience with adjusting the amplitude of waves on a daily basis. As you adjust the volume on your phone, computer, or television, what you are doing is telling your device to increase or decrease the amplitude of the sound waves being emitted. For my performing musicians out there, now would be a good time to thank your amplifiers for all their hard work in adjusting the signal wave's amplitude for you. Here again, we will define amplitude as half the difference between the maximum and the minimum of a sine wave. Algebraically speaking, however, amplitude is simply a dilation of the sine wave. From geometry, dilations take a set of points and multiply them, in our case, by a singular constant value that here we are calling amplitude. This adjusts our output values, and so we're going to move amplitude in front of the function as a scalar multiplier of the function.